In measure theory, and in a rigorous treatment of probability theory, sigma-algebras play a central role. The definition is pretty simple, but working with sigma-algebras may be challenging. It may help to clarify what sigma-algebras really are and why we insist on using them. We shall in this presentation mostly discuss sigma-algebras from a probabilistic perspective. Given a set omega, a collection of subsets of omega is a sigma-algebra on omega if omega itself belongs to the collection, and for every set in the collection also its complement is there, and for any sequence of sets in the collection also their union belongs to the collection. In words, a sigma-algebra on omega is a non-empty collection of subsets which is closed under the set operations of taking complement and countable unions. There are various reasons why we want to work with sigma-algebras. To begin with, a probability space is a triple that consists of a set omega, a sigma-algebra on omega, and a measure that assigns probabilities to the sets in the sigma-algebra. We use probability spaces to describe experiments of a random nature. The sigma-algebra in the probability space corresponds to the collection of sets that we allow ourselves to measure or assign probabilities to. As an example, consider the experiment of tossing a coin twice. The possible outcomes of the experiments are the outcomes heads heads, heads tails, tails heads, and tails tails. Given any set, the following are always sigma-algebras on that set. The trivial sigma-algebra containing only an empty set and the set itself, or the power set containing all subsets of the set. In the above example, the former sigma-algebra would be way too small, since it wouldn't allow us to assign probabilities to any meaningful event, but the latter would be suitable. When constructing a probability space, the collection F corresponds to the collection of sets we are allowed to measure. The requirement that F is a sigma-algebra makes sure that we never leave F by means of the usual set operations. We want omega itself to belong to the collection to make sure it's non-empty and that the maximum probability is always 1. Second, if we want to measure a set A, then typically we also want to measure the probability that the set does not occur. That is, we want its complement to belong to the collection as well. Also, if we want to measure two sets A and B, then typically we want to measure the probability that either of the two occurs. That is, we want their union to be in the collection. Finally, taking finite unions is not always enough. Consider the example of tossing a coin until heads. The set of outcomes can be described as heads, tails heads, tails tails heads, and so on. All these individual outcomes are interesting, but also the event that an even number of tosses are required until heads. This event is a countable union of the individual outcomes. And yes, a sigma-algebra is also closed under countable intersections, as those can be rewritten in terms of complements and countable unions. If a sigma-algebra is mainly introduced in order to keep track of which sets we're allowed to measure or assign probabilities to, then we typically want it to be large. If our sample space is discrete, that is finite or countable, then we would typically want to assign probabilities to all individual outcomes. As an example, consider the roll of a die. The different outcomes are the values 1 to 6, and these are outcomes we would like to assign probabilities to. A suitable sigma-algebra in the discrete setting should therefore contain all the singletons, that is, sets containing only one element. If omega is a finite or countable set, then the smallest sigma algebra that contains all singletons of omega is the power set, the set containing all subsets. When omega is finite or countable, the standard sigma algebra on omega is therefore the power set. In the continuous setting, the power set is no longer a suitable sigma algebra. Suppose that we want to construct a probability space that corresponds to the uniform distribution on the interval 0, 1. We then set omega to be that interval and want mu to be a measure with the following properties. First, we want the probability that mu assigns to an interval to be the length of that interval. Second, we want the measure to have the property of countable additivity. Finally, since the probability of a set corresponds to some notion of length of that set, then if we shift the set horizontally by adding a number r to each of its elements, then the probability of that set should not change, because by shifting we do not affect the length. As it turns out, there is no function mu defined on all subsets A of the interval which satisfies these three properties, at least not if we assume the axiom of choice. So, in the continuous setting, we cannot expect to be able to measure all sets. The solution is to restrict ourselves to a sigma algebra which is large enough to contain all sets we may want to measure. When omega equals the real line, or some interval on the real line, the typical set we want to measure is not a singleton. We rather want to assign probabilities to intervals. Given an interval I, the smallest sigma algebra that contains all open subintervals of that interval is known as the Borel sigma algebra on I, and is denoted by B of I. One may show that, for the interval 0, 1, equipped with this Borel sigma algebra, there exists a unique probability measure where the measure of an interval is its length. This measure is known as Lebesgue measure and corresponds to the uniform distribution on the interval 0, 1. Because of this fact, in the continuous setting, the Borel sigma algebra is the standard choice. We started out with the observation that we may run into problems in trying to assign probabilities to all subsets of a sample space. In the discrete setting, this is never a problem, but in the continuous setting it is. By restricting ourselves to sigma algebras containing all sets we may want to measure, this problem is resolved.